Okay, let's have a little look at the exponential function. So the exponential function is a relationship in the form of y equals a to the power of x. The base, so a, always has to be a real number, and it's a number not equal to 1, and x is the power or exponent. So y equals a to the power of x. That's the kind of form we're looking at here. So if I was asked, for example, to graph y equals 2 to the power of x. This is how we go about doing that. Pretty simple. We do a little table of values here. Now I'm going to just pick boundaries, so to speak. So I'm going to start at -4, 2, 1, 0, 1, 2, 3, and 4. All we need to do to fill out this table of values is finish off the value for y based on our exponential function in this form up here. So 2 to the power of x. So anything to the power of 0 is going to be 1. That will be 2. This will be 4. That will be 8. And that will be 16. Going back the other way, because I'm going to negative power, we pretty much do the same here. It's just we put it under 1. So going back in this direction here, instead it's going to be 1/2, 1/4, 1/8, and 1/16. So this is the table of values to represent y equals 2 to the power of x for our exponential function. Now, if I was to draw this, forgive how crude this is going to end up being. 1, 2, 3, 4. That's really it's 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15, 16 at the top there. So it's going to be 0 down here. That'll be 16. That'll be 1, 2, 3, and 4. That's my x. That's my y. Being careful to label everything properly. If I was to map this little table of values here, well, I'm starting when x equals 0 here. So x equals 0, y is going to equal 1. So it's going to go through here. Moving over 1, it's going to be at 2. It's going to be here. Moving over to 2, it's going to be at 1, 2, 3, 4. Moving over to 3, it's going to be at 8. And then we are all the way up here. Now, if I keep moving back this way, you notice it gets smaller and smaller and smaller. So it's going to go all the way down like this. So if I was going to draw my graph now, you see it's a curve that increases exponentially. So it's increasing exponentially as we move along the x-axis. So this is the graph for y equals power 2 to the power of x. Now there's a couple of features about this graph here. The first thing is a thing called an asymptote. So in this graph here, y equals 0 is the asymptote. So I'll write that as. So the asymptote essentially means a value that it approaches but will never ever ever reach. So my asymptote for this graph here is y equals 0. And it's going to be a horizontal asymptote here as well, because it's approaching something horizontally, but it's never ever ever going to make it. You see vertically, it's going to keep going up, keep going up, and keep moving down. But horizontally, it's going to constantly approach y equals 0, but never ever ever make it. So this has a horizontal asymptote of y equals 0. Now, if I was to graph another function here, so y equals, say, 3 to the power of x, that would, you notice something to the power of anything at 0 is always going to be 1. So it would go through the same exact point here, except this is how, because it's a bigger number, it means as these numbers go to a higher power, it's going to increase faster exponentially. Now, I'm just going to guess, but I know that if I had something that was y 3 to the power of x, it's actually going to be steeper, is the best way to probably describe it. So the bigger the base value, the steeper your graph is going to be. Now, there's a couple of things that happen when you add a few things to a function. So I'm going to rub this out. Now I'm going to draw just a really basic idea of y equals 2 to the power of x, the one that we just graphed. Now we know it looks a little something like, I don't know, that. So there. We know that this looks a little something like that. Now, forgive me for not filling in all the spots, but I just want to illustrate a couple of points here, because there's a couple of things that we can do with this equation here. The first thing I'm going to look at is a vertical translation of the graph itself. So let's say I had this y equals 2x, but I'm going to say plus 3 in my equation. What does this plus 3 actually do? Well, it moves every point of my graph up exactly 3 units. So from here I go 1, 2, 3. So it means it'd go through there. Now my graph is going to be exactly identical in shape. It will be identical in shape because if I was to do a table of values for that, the power doesn't change and the base doesn't change. So the shape of the graph is going to be exactly the same. Adding this plus 3 is a vertical translation. All it means is that every single point in this graph here is going to be the exact same distance apart as you move up or down. Okay? So vertical, or this plus or minus 3, whatever it is, just changes the vertical translation. And the only other thing here is that this graph here, we know the asymptote is y equals 0 because it approaches 0. Because we've moved everything up 3 units, the asymptote for this graph is going to be y equals 3. So that's your vertical translation by adding that little number on the end. Now, there's also something else you can do. So let's pretend I had this graph here, so I've drawn a little bit lower down the bottom. So let's again go to that, go to example, y equals 2 to the power of x, looks something like that. If I had y equals negative 2 to the power of x, that actually gives us a reflection on the x-axis. So it would look something like that. Again, exactly the same shape, it's just reflected from the top. Now this means both of them still have a horizontal asymptote of y equals 0, because they both horizontally are approaching, they're both approaching y equals 0, but they'll never, ever, ever touch it. So this is reflection. If you've got a negative base, it just reflects that graph. It flips it on its head, essentially. And it leaves us with one more type, or one more thing you can do with these graphs. And that's going to be, as you probably can guess, it's going to be our reflection on the y-axis. So again, I'm going to draw my trusty y equals 2 to the power of x. Now, if I had y equals 2 to the power of negative x, all that does is, again, exactly the same shape, and they'll cross over at the exact same point here on the y-axis. But, as you see, it's reflected over the y. So when you have a negative power, it reflects it over the y-axis. So the 2 steps to essentially graphing these would be to create a table of values, graph it, but by the 3 little traits, the plus on the end, the negative out the front of the base, or the negative power, if it's going to be flipped on the x, on the y like this, or if it's going to be translated up and down. Pretty straightforward stuff. Now you might get a question that says something that, a function is represented, or a function of x is represented by 16 to the power of something. And it might say, okay, well 16 to the power of something equals 32. Find out the value of x. Well, all you would need to do is draw a table of values here, like that. You would do, well, y equals 15 to the power of x. So I'm going to go 0, 1, 2, 3, negative 1, negative 2, negative 3. You would fill out those values, you'd graph it, and have a look. You'd go up 32 on the y-axis, and then see where it actually collides. And that's how you would find your value. But that is essentially everything you need to know about the exponential function. It increases exponentially. It can be flipped on the y-axis or on the x-axis, and it can be translated up and down. Pretty straightforward.